Welcome back to App of Core 2025. After day 9, I completed day 10 and 11 now because day 10 was quite tricky. So I'm just going to go through the solution here. But first, let's check the question. Day 10, factory. Just across the hall, you find a large factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. All that remains of the manual are some indicator light diagrams, button wiring schematics, and voltage requirements for each machine. For example, we have this hashtag code 3132230 blah blah, and then something in squirrely brackets. The manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics in parentheses, and voltage requirements in curly braces. To start a machine, its indicator lights must match those shown in the diagram where dot means off and hashtag means on. The machine has a number of indicator lights shown, but its indicator lights are all initially off. So an indicator light diagram like dot, hashtag, hashtag, dot means the machine has 4 indicator lights, which are initially off, and that the goal is to simultaneously configure the first light to be off, the second light to be on, the third to be on, the fourth to be off. So here, off or on, off. You toggle the state by pushing any of the listed buttons. Each button lists which indicator light it toggles, where 0 means the first light, 1 the second, and so on. When you push a button, each listed indicator light either turns on if it was off or off if it was on. You have to push each button an integer number of times. There's no such thing as 0.5 presses, nor can you push a button a negative number of times. So button wiring schematic like 034 means each time you push that button, the first, fourth, and fifth indicator light will all toggle between on and off. If the indicator lights were hashtag pushing the button would change them to this one. So you have 0 goes off and then 3 and 4 goes on. Because none of the machines are running, the voltage requirements are irrelevant. It can be safely ignored. So this in the back we ignore. You can push each button as many times as you like. However, to save on time, you will need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. There are few ways to correctly configure the first machine. You could press the first 3, blah, blah, blah. So you can press all these different buttons a variable amount of time to end up at this state. Then you find the minimum, and the minimum is 2 in this example. One way to do this is by pressing the last 2 buttons once each. The second machine can be configured with as few as 3 button presses. One way is 0, 4, 1, 2, 0, 1, 2, 1, 2, 3, 4, once each. The third machine has 6 indicator lights, and it can be done in 2 presses. So then the fewest button presses required to correctly configure the indicator lights on all the machines, because they're all independent, is 2 plus 3 plus 2 is 7. What is the fewest button presses required to correctly configure the indicator lights on all of the machines? So here we have all of them. Each line is an independent machine. So we just have to go through all of them. And this is quite a nice puzzle. Let's go through how I did it. So for each line, I take the part before the square bracket and remove the opening square bracket. Then I have the pattern. So it's just whatever is between the square brackets. Then I have empty pattern is the same length of string, but all off. So a map. the length of string to dot, and then join it together again. Then for the buttons, I go through the list of, after the square bracket, drop the last one, get the string for each button, remove the prefix and suffix of the normal parentheses, and map these numbers within each of those buttons. So this is one button and this. So each button is a list of these ints in the button. Then I have this. So button is a list of int. And then the joltages, I just map the list where between the squirrely brackets, I get the integers. Then I have my representation, which is, it has a pattern. A pattern is just a string. And then I have an empty pattern, and then the goal pattern that I want to reach, the buttons, which is these buttons, which is a list of int. Maybe I'll just do int. Like this. Simplify it. So button is just a list of int. The pattern is a string. Okay. So I have this. The two patterns, the list of buttons, which is also int, and the joltages we can ignore for now. Then I say, hey, I want to collect the button presses. So I have a list of ints. So I go through each diagram, and then I loop while not done, increase how many buttons I press. So then I look at, given this list of buttons, which is a list of int, give me the combinations that are of size times and basically this gives me, based on the list of whatever this is, the t, so it's a list of int. Gives me a few lists of int where I have all the combinations of, let's say I want to have all the combinations of 1, then I get all the combinations of how to press one button. And that's kind of boring. It's just each button once. And then if I have 2 here, then I get all the combinations of 2 of the different buttons. So I can press the first and the second button, the first and the third button. I don't want to press the same button twice, because pressing 2 buttons twice is the same as not pressing it. So that's why I filter it out, as long as it's not in the current combinations. So if it's in, I don't map it. If it isn't, I map it. I just extend this, and then recursively I get the list. So, where were we here? So get the buttons. Maybe I can go like this. With times like 1, my combos are basically each button once. So first button, then second button. So if I go here, that's probably the first button is 2, 9. And there's one button with a 4, and then there's one button with a 3, 5, 6, 7, 8. So those are the elements that I get here. One with a 4, one with just a 4 in it. This is size 5 is the 3, 5, 6, 7, 8 one. So each button once, and then I try see if any of those combinations, I go through all of them, if when I take the empty pattern and I press those buttons, if the result matches my goal pattern. So what does empty pattern dot press is? So empty pattern is dot, 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 the length of the pattern. And press, what does it do? It goes through the list of buttons and presses the button and adjusts the pattern based on the outcome. So for each button, I go into the pattern that I have, which is just a string, and flip all the integer, all the yeah, this should have been restayed IDX, and flip all the indices from that button. Oops. So if this button has 1 and 3, then I flip the index 1 and 3 in the pattern, and then I return that. So then I can just simulate getting all the combinations for pressing 1 button, getting all the combinations for getting 2 buttons, try all of those combinations by pressing all the button within each combination, and checking if the result is mapped, if it's correct, if it's what I want to get, which is the pattern here. For example, here I start with the empty pattern, dot dot, and I press the buttons, and then I want to see if the pattern that I get out of the button presses matches the goal pattern, which is hashtag. If I'm done and finished. So I get out of my while loops. I know that I can do it with this amount of times. So I add button presses dot add times, add the number of times to my list of button presses. So at the end, maybe here, I can see that the sum of button presses is, okay, I probably printed it somewhere here now. Console 5 to 7. So I can do a sum up when the fewest number of button presses required to correctly configure each, like all of the indicator lights is 5 to 7. So that's part 1. Then we can go to part 2. And here it gets really wild. So part 1 I was able to solve. Part 2 I had to look at the math of it and figure out how to solve it with basically an external tool. But let me explain. All of the machines are starting to come online. Now it's time to worry about the joltage requirements. Each machine needs to be configured to exactly the specified joltage level to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage levels. Ignore the indicator light diagrams. The machines each have a set of numeric counters tracking its joltage levels, 1 counter per joltage requirement. So now we're looking at these joltages. The counters are all initially set to 0. The joltage requirements like 3, 5, 4, 7 mean that the machine has 4 counters which are initially 0, and that the goal is to simultaneously configure the first counter to 3, the second to 5, the third to 4, and the fourth to 7. The button wiring schematics are still relevant. In this new, so the button wiring schematics are this part. This new joltage configuration mode, each button now indicates which counters it affects, where 0 means the first counter, 1 means the second counter, and so on. When you push a button, each listed counter is increased by 1. So now we're not toggling the lights, we're increasing the counter with each click, so we can press a button more often as well. That's relevant now. So button wiring schematic like 1, 3 means that each time you push the button, the second and fourth counters would increase by 1. If the current joltage level were 0, 1, 2, 3, then this would increase to 2 and this one to 4. You can push each button as many times as you like. However, your finger is getting sore from all the button pushing. And so you will need to determine the fewest total presses required to correctly configure each machine's joltage level counters to match the specific joltage requirements. Consider again the example. Same example, configuring the first machine's counters requires a minimum of 10 buttons. Then how to do it? Configuring the second requires 12 and then 11. So the fewest button presses required to correctly configure the joltage level counters on all the machines is 10 plus 12 plus 11 is 33. Analyze each machine's George's requirements and button wiring schematics. What is the fewest button presses required to correctly configure the voltage level counters on all the machines? So now basically we can ignore the first part where we were toggling the light. Now we're interested in this last part, the voltages. And basically the question is, how often do I press each of the buttons? And I can't do it with combinations. You can quickly see here that I want some of them to be really high, like 59. So there's a really large amount of combinations of button clicking to test if I want to test all of them. So I quickly run out of space to test all those combinations or time to run through them all. So then the next thing to do is look closer at the problem. So relatively quickly, I figured out that it is kind of like a math equation where I have in this example 1, 2, 3, 4, 5, 6 buttons, and I have 4 different numbers. So I have 0, 1, 2, and 3. And these number slots, 0, 1, 2, and 3, are the ones that I need to in the end have set to the correct amounts. And the buttons, these 6 buttons, the question is how often do I press each of them? So if you look at this, you can put coefficients in front of these buttons, like I did here, A, B, C, D, E, F, and say, this is an equation. I need to know what is A, what is B, what is C, what is D, what is E, what is F, how often do I press these buttons? So that the right side of the equation holds, which is 3 times the 0th, 5 times the first, 4 times this one, and 7 times this one has increased. And then when you shuffle it around, so you can apply simple math and say B13 is B1 and B3. So basically it's all plus between here, but let's just leave it like that for looking at it. Then the right side is the same. Then I can see that I can scoop these back together. So A, B, and D are all relating to button number 3. So I know that A, B, D, adding those together gives me the amount of how often I will have to increase the value in the third, which is 7. So I know A, B, D is 7. And then similarly, I have B plus F is 5, and so on. So I have all these equations based on the coefficients of the buttons. And the other thing I have is I can just increase. So each coefficient is greater or equal to 0. Each button is pressed 0 or more times. I don't know what this was, ignore this. So I first tried this also with mapping it to equation and then trying all the options still, but it still was way too slow. So the real mathematical way to map this is to implement the simplex algorithm. And the mathematical area for this topic is linear programming. And specifically, it's linear programming is also rational numbers, so between 0 and 1, but we also want all to be integers. So the subset is called integer programming. That's a operations research or mathematical optimization problem. So it's integer linear programming, where you basically have exactly these kind of equations. I want to maximize or minimize something. subject to constraints. And there's ways to implement this. I don't know. I didn't do it now. What I did instead is use a library. So the first thing I tried was Apache Commons math library, but this one just does linear programming, so not includes integer linear programming, where all the results are integer values. So then I switched to using OR tools Java, so operations research tools Java from Google, and that did the job. So the strategy is to map this input that I have, we parsed it and we map it to equations. And then we can use the simplex solver when we set up our equations and constraints to give us a solution. And then we know what's the minimum, what's the optimal for each of the equations. So I have an example here. If I run this, let's go through it. It takes a bit to load this. Actually, I maybe don't want to debug it because it might be too slow. Let's just run it. And I think I printed it already. Yeah. So I have an example here in the top. So I have all my diagrams, same setup as before. And I print the example. So the example is this, the empty pattern is this. Okay, we can ignore the patterns. We have these buttons, 10 buttons, I think. And then the voltages. And then similar to our previous example, where, or maybe I can even show that one. I'll just show the example one, it's way nicer. So I have 6 buttons that I just showed and the voltages. So this is the same as we looked at here. Then what I want is these equations. So here you can see I map exactly these equations that I have in the top. I map them in the code as well. And how do I do it? First, I just make a list of the coefficients that I might be needing. Then I take the amount of coefficients. So in this case, 6. Can have 6 buttons, so I need 6 coefficients from my list. These are the variables. And based on these variables and the buttons list and the voltages, I can build equations. And the equations are, so it will be a list at the end with 4 entries where I have, in this list, I have pairs of a map and a double. The map is just basically this, E1, F1, and the double is the 3, so the other side of the equation. So then what I do, I make a list of the size of the equations, which is the size of how many voltages I have, in this case 4. Then I go through each button and say, okay, here, this, each button gets its own alphabetic variable name, variable, as we said earlier. And then for each entry in the button, which is a list of voltages, right? The voltages index. This gives me the index. So for example, I have 1 E and 1 F equals 3 is the equation. Then this will have this will relate to the voltage for the buttons 5 and 6. So I go into the equation and say, in this button, I will have, actually, which one do I have in the E and F? E and F. here have 0 and 2. So the first outcome and the third outcome. So I go to that voltage index. Those are the buttons. So the example is actually button is 0, 2. So I go to 0 and 2 in my voltage map and add the variable name E and F, which, because this is like the last two buttons, I add a 1 to them. So then I get the 1 E plus 1 F condition. This is mapped into this map. So then at the point 0, I have an E. And then at the point 2, I have an E times 1. Now at the end, I map this 1 E plus 1 F to the actual voltage. So I just go through the 4 voltages in this case again and say 1 E plus 1 F 2, 3. I wonder if I can debug that, or if it's too slow. Okay, this one works. This is my example that I'm interested in. Button has just 3. No, I wanted the one with 0 and 2. Are you? Guess this one. 0, 2 here. So now I have the fourth button. No, index 4, so the fifth button. So this one, 0, 2. What do? I have this button gets the variable E. So yeah, this button is this, and it gets variable E. And this is actually a bit different than. And then for 0 E, I map 1. And for E2, I map 1. Like that. So then I have E and 0, and so I mapped E into the zeroth Georgia equation map and into the second Georgia equation map with a 1. Kind of like more like this. The second equation map. And in the end, when I loop through the map again, I end up with 1E, because I mapped it here in the first one, and 1F. Okay, now I'm the third one. 2, 3. So it comes from a different place actually. If I go again, so this equation, let's just track this equation down. 1E plus 1F is 3. So I'm interested whenever 3 is used. E, okay, this is what happens. This is where the 3 is coming from, so I confused the 3 with this 3. The 3 is in the 0th place of the Joltage map. And E maps 0 and F maps 0. And that's how we get E plus F is 3 relating to the 0th index of the Joltage map. So let's go through the example again, where we do actually map 0th jolt index and the second jolt index. We map the E here, and then we also map 0, 1 or something with variable E, variable F. Let's just ignore the other part. 0th jolt index 0F. So now we can look for that. So we go through. Okay, what happened? Let's start again. A, B, C, D, D again, E. Okay, here's E. E, we map the jolt in the 0. We have the button 0 and 1, 2. So we map E and 0 to 1. Then we map E and 2, but we don't care about that. And then we map F and 0 to 1. So then what happens is in 0, we have E1 and F1. If I go here, this is the 0th index, the jolt index 0. I have in the equations map E to 1 and F to 1. And these are the other ones, the other equations. So these are all the equations. This is probably the easiest place to show it that we had up here. So these are all mapped into these pairs. This type is a bit confusing, but we can see it here. EF1, VF1, and so on. Then we return that to here. So then we have this list of equations. And this is the part that's pretty slow. Also printing the equations. So let's just print it all. So here I'm printing the equations and then it slows down because it goes into the solving. So that's so we know how to build the equations now. This is kind of the slightly confusing mapping part, but it's all good. Then this is the part that takes long. We go into this OR tools territory. The way this is implemented is not in Java, but in some other bindings, C++ or something. So we have to load these native libraries so that the linker knows if I call these methods what actually to run. I create a solver, which is, I use SCIP solver here for this specific problem. Then basically I can use these variables and equalities to set up this problem. So basically we have one of the conditions was that each coefficient is greater or equal to 0 because I can press each button 0 or more times. And it has to be integer now. So that's why we use this solver, the MP solver. What do? We say between 0 and infinity, we map this variable. Then we have these MP variable list. Then we add the equalities, which is basically an inequality, a constraint with a lower bound and upper bound, but both bounds are the same. So we map these equations that I just talked about based on their coefficients and values as constraints. I don't know why I did this refactor. Then I check which variable index matches for the coefficient and set those coefficients into the constraint as well. So the solver then knows about these constraints as well. So the solver knows about the int-var and the constraints. Then we just have to say, so there's a nice part about this, pretty easy. Once it's all set up, we just say, hey, minimize the sum. How to say minimizing is we pick the objective, say we want to finalize the setting of this coefficients for the objective, which is it is the variables, setting them to 1, and then we set the goal of this solver to minimize, and then we just say solve this for me, please. Then we want the optimal result, and we can pick it out. So the solution value gives me the optimal result. Then I round to int, so each variable, so in our case it was 6 different ones, A, B, C, D, E, F. Each one has an optimal one based on minimizing all of them. So the minimizer here is basically this. How do I get the lowest amount of button clicks? Is I say for each button, so each variable, each button has a variable name, right? For each of those variables, I say set it to 1, which means if you sum up the button clicks, so the sum of the button clicks amount, that's what I want to minimize. So that's what kind of this says. It doesn't just minimize, it minimizes the sum of x, where x is variables. So 1 time each variable. So we want to minimize that sum. Then we get the smallest amount of button clicks that has a valid solution given our constraints that we set. And then we can sum, so the same sum that we're minimizing. So we're outputting, so we kind of get the output for all the variables, but we just want the sum at the end. And then in this example, we get 33, like here. And then for the real result, for the real input, we get a large number, 19, 8, 10. Here we go. So we have 19, 8, 10. And yeah, that's basically it for day 10. I don't know how to solve it computationally, except for implementing the simplex algorithm yourself, which would be maybe interesting to do. But yeah, it was also interesting to try out using the solver library and just make sure I can map the inputs to the solver and get the solution out of it. So that's it. Enjoy the rest of your day.